Welcome to the Earth Science Classroom. We are in the Earth's Interior series, and this video is all about the crust. The crust, the surface that we exist on, dig through, obtain minerals, fossil fuels. We build our houses and structures from its raw materials. We buy it, we sell it, we trade it, we lease the land on it, we grow crops in the soil, we buy land and sell land, and everything is to do with the crust, that really tiny thin area of the earth. Now, in terms of thin and the earth, it is 0.005 times the width or distance or thickness of the earth. So in reality, this is a extremely thin kind of like skin almost of our planet. The crust is, as I mentioned in previous videos, it is rigid. It is solid rock. It does move through convection currents and crustal movement and tectonics, but it is generally rigid. Now, in terms of the seismic waves as the most conclusive evidence we have that our Earth's interior is of different densities, certain thickness, everything, the boundaries or the layers are defined by the changes in these seismic waves recorded from earthquakes. Now, the changes, when it changes velocity, these are called discontinuities. And what happens is it's usually the seismic wave or the energy wave that's passing through a certain medium or certain area of the Earth's interior will be refracted or bent. Either it will increase in velocity or it will decrease in velocity depending on the density of the rock. Now, generally, as density increases, these velocities increase. Now, with depth, going down here is the arrow on the left, you see, with depth, generally the density does increase. Now, density of the crust, with the ocean crust being here, oceanic crust being the average 3.0 grams per centimeter cubed, and the continental being pretty much 2.7 grams per centimeter cubed. So again, as you increase in depth and go deeper towards the inner core, you will get an increase in density, also due by lithostatic pressure, gravity, and the force applied, which is all based on the pressure. So think of the crust as the exterior layer, but really the main difference that separates the crust from the lithosphere, or it gives some sort of like definitive boundary, really, is this red line that is the moho. Now, talking about seismic waves, this was the first one that was really discovered in 1909 by Mohorovich, that the seismic waves, when they went through the crust, whether it's ocean crust or continental crust, they would increase in speed from an average of 6 kilometers per second in the crust to an average of 8 kilometers per second. So there is an increase of 2 kilometers per second between the very top part of the crust and the density of the materials in that crust, be it basaltic rock for the oceans or granitic for the continents, you get that increase in density in the lithosphere. And that went down to an average of 100 kilometers, but it got deeper underneath the continents due to isostasy. So the moho really separates the crust from the lithosphere, and the lithosphere really is, termed the mantle. So it really is the crust being the top, and then the mantle starting here and then going down from here. And the mantle is the largest by volume of the Earth's interior layers. So it's around 82% of the volume of the Earth. So it does take up a large part. Now we know the mantle in terms of its physical layers being differentiated by the pressure and the density and the temperature and how those different physical properties affect the mantle, would actually divide it into the lithosphere right here. So L is for lithosphere. And then the oceanosphere down here. And below that would be the lower mantle or the mesosphere. But we're going to look at the crust in more detail today. So I'm just going to draw a little line down here to separate. On this side, I have the ocean crust described on the left. On the right, I'm going to discuss the continental crust. So the ocean crust, okay, in terms of the comparison and contrasting, I just do with my students, I just do a little like table, and we go through the general characteristics of each of the crusts. So obviously, I have already stipulated that the difference in density is clear. So this is denser. This is less dense. Again, try and stay clear of the word lighter because it's really misleading. This is still a large, million tons of rock, basically sit on top of the Earth, on top of the mantle. So it's less dense, so denser. It is basaltic and granitic in terms of its composition. So its composition really is more of the silica or silicon and magnesium. Occasionally, they call this the seamer part of the lithosphere, which is the oceanic crust. Whereas the continental crust is basically 35% of the Earth's crust. And it's usually some silicon and aluminum. So they call it seal or sial. So seamer and sial or seal. Okay. So there's differences, but obviously there's a lot of similarities in terms of the base. Now, the base of the continents, you do get some increasing percentage of basaltic rock, obviously because of the where it comes from in terms of the rise in magma and convection currents, but you do get a small amount of basaltic rock, igneous rock at the bottom of the continents. So the oceans are generally younger, very young in comparison. So they're younger. So they are basically part of the Wilson cycle in terms of its cycling of material from birth at the ridges to death at the subduction zones. And the maximum is around 180 million years old. And that's generally in the Pacific, as it is the largest ocean basin, therefore the longest distance from ridge to subduction, therefore the longest time it exists for. And then on the opposite side, obviously, the continents are older, and that reflects in what's called the continental shields. The shields are the dome-shaped or shield-shaped, very old part of the continents, usually more central part of the continents away from the continental margins and obviously the oceans, but they are, up to 4 billion years old. And certain shields, the oldest ones would be the Canadian and the African shield. Now, the shields that are a bit younger, Brazilian shield, there's also the Australian shield, but Canadian and African are the oldest. Even though they did find zircon crystals in Australia, which are dating back 4.2, 4.3 billion years old. So we have clear differences here. But there's one important similarity that we have to get across to the students, is that unlike other layers in the Earth's interior, the asthenosphere, lithosphere, mesosphere, into the core, you have, differences that are purely vertical, based on density, pressure, and temperature, purely vertical. However, the crust is the only real layer that has differences, it's in red, differences that are both vertical, differences in physical and chemical properties, but also lateral. There is differences as you go from side to side, or basically laterally through the continents or ocean crusts. You have these differences based on locations. So it is the only area where they are both going to have differences both vertically and laterally. All right. Another similarity is on the very top of the crust. Let's say the top, few hundred feet, maybe down to 1,000 feet, or even a few thousand meters. You're going to have at the very top of the continents, you're going to have horizontal layering, or what's called bedding, or strata of sedimentary rocks. Now, in terms of geologic time and geologic principles and laws, these are laid down through various processes we'll get to later on. But both the continent and ocean crusts are primarily at the very top of the surface, primarily sedimentary, especially ocean crust, because most sedimentary rock are formed through a water environment. Now, that could be lakes or rivers, but mostly involved with oceans. So there is definitely a comparison there and a similarity there. Okay. Now, what I've drawn here is like an expanded, larger view of this circle area on this crust part here, where I've expanded it to show that, here's the ocean up here, and this top layer will be sedimentary rock, maybe limestone, maybe calcium carbonate deposits, maybe some different kind of shale, all that kind of stuff. But below it, what you have is right here, you have pillow basalt. Now, this forms at the ridge, and the way it forms through a pillow is it expands and forms like little pillows on the ocean floor, these large vertical columns of pillow basalt. And below it, you'd have some gabbro in the green. And then below that, you might have some andesite, that intermediate igneous rock right there. So you have these different layers, and it's very consistent with the ocean crust, whereas the continental crust would be a mixture of some diorite, some basalt at the bottom, maybe some andesite in there as well, but a lot of granite, a lot of different variations of granite, and different mixture of the minerals, the 5 minerals with the mica and the feldspars and the quartz. So you get this big mixture, this big soup bowl and mixture with the continents, whereas the ocean crusts are kind of like more uniformed and structured. So I hope this helps with dissecting the crust in terms of the two divisions, the oceanic and continental. And if you like the video, please subscribe, and look forward to the next video.